Welcome everybody to the 2022 Ingenium Professional Development Seminars. On behalf of Engineers Geoscientists Manitoba, I am Gemma Keach, Events Coordinator for the Association, and I'll be the moderator for this final session of today, and indeed the whole conference. This is it. This is the last one. Throughout today's presentation, we encourage you to send in any questions you may have for the presenters via the chat. Please note that this presentation is being recorded and will be available through the Ingenium Hub until January, along with all of the other presentations from this week. So do go check that out and revisit the sessions that you may have missed, as well as our exclusive on-demand content that you can find at the bottom of the Ingenium Hub. So this final session is a little different from most of the other Ingenium sessions in that we have not one, not two, not three, but four presenters. And while they're all going to enlighten you on different topics today, they have one thing in common: the Engineers Geoscientists Manitoba Innovation Award. So for those of you that don't know, each year our association honors individuals and companies through a variety of awards. And this particular award is intended to highlight the innovative work being done within the province by engineers and geoscientists. This year, 2022, was the first year that we've accepted nominations for the new Innovation Award, and you're about to hear from the three projects who made the 2022 shortlist. So how this is going to happen: we're going to have a short presentation for each of the projects from the project leads, followed by an opportunity to engage with those speakers through a question and answer session for each project. So it'll be a project presentation, project Q&A, and then we'll move on to the next project and another Q&A. So definitely throw those questions in as you're watching the presentations, and then we'll get to those questions at the end with each of the presenters. So let's dive straight into it. It is now my great pleasure to welcome our first presenter of today, Colin Gilmore, whose team was shortlisted for their grain bin imaging innovation called GrainViz.
All right, good morning or good afternoon to everybody. I am Colin Gilmore. I'm a professor of electrical and computer engineering at the University of Manitoba. I'm here to give a presentation on grain bin imaging. So it's using electromagnetic waves to image the interior contents of grain bins. The product that is sold commercially for this is called GrainViz, so that's why it's in the title of the talk. I'm representing a much larger team that has worked on this technology over more than a decade. So there's three other professors from the University of Manitoba: Joe Levetri, Ian Jeffrey, and Jitendra Paliwal, two employees of AGCO Corporation, which is the corporation that sells GrainViz, the imaging technology, Braden Pierce and Mohammed Asefi, and also Paul Card, who used to be with AGCO Corporation until very recently. My talk, I'm going to introduce the group a little bit more clearly with some photographs and give a bit of the background story. The second thing I want to talk about is why should anybody care about monitoring grain? And that's a big important thing that I would like to talk about. Then I'll show some of the hardware, the algorithms, some of the imaging examples that we use in this grain bin imaging technology. So the grain bin imaging itself, the idea was generated at the University of Manitoba and then commercialized in a startup company called 151 Research that was eventually sold to AGCO Corporation, which is a large agricultural company. And so the electromagnetic imaging lab performs this kind of imaging on many different ranges of targets. And so there's myself, Colin Gilmore, Joe Levetri, and Ian Jeffrey are the current main members of the electromagnetic imaging lab. And we started working with Jitendra Paliwal down here from the Grain Storage Research Lab at the University of Manitoba, who made the connection of, could you ever do this in a grain bin? And then over here, we've got Braden Pierce, Mohammed Asefi, and Paul Card. We're part of the team that commercialized the technology inside of the startup company. And so while I'm the author of this presentation, this is obviously the work of over a decade of these people and many more. And I'd like to recognize them. So myself, I'm an electrical engineer, and I had no idea the complexities of grain storage before I started this project. So I used to think, you harvest grain, you just throw it in a big steel container, great, you're done. You just pull it out when you need it. The problem is that grain can and regularly does spoil in a bin, and it's a very complicated process as to what happens. And so there's, depending on the outside temperature, the temperature of the grain that's harvested, the moisture content of the grain when it's being harvested, all of these things can lead to storage problems where the grain goes bad. And it can go catastrophically bad. So you could lose the entire contents of a bin, could become worthless. And even worse than worthless is that once it does spoil, it often solidifies and you can't get it out. It becomes a terrible problem. In the most catastrophic scenarios, it actually can light on fire. So the grain itself it has a loss of energy stored in it, which is why we want to eat it, is we want the energy from the grain. But if that energy gets released inside of a tight enclosed container like a grain bin, and the surrounding grain insulates it, it can actually spontaneously combust and start on fire. This is an example photograph of what can go wrong. So it's actually the grain, there's many things that can go wrong, but this is the most common one, is that the grain decides, given temperature, certain temperatures and humidities, the grain decides, I'm in the ground, it's time to sprout. It's the springtime and I should start growing. That process releases heat and moisture, which causes the surrounding grain to also think that it's time to sprout. And then it releases heat and moisture, which causes subsequently and on. And it's a positive feedback process where the grain starts to spoil. So you can see here that the moisture or the high temperatures are on the top layer. It just starts to grow. It becomes a grass. This is, I think these are oats that started to spoil. And you can lose the entire economic value. So grain has to be monitored, and there's several different ways of doing that. So this is one of the older ways. I mean, the most basic way is if you go back to this bin here, I mean, if someone just climbs to the top of the bin and looks in, which could be 130 feet in the air, they can be very large. But if you just look into the bin, you would notice, this doesn't look like oats, it looks like grass. So, that's the most basic way, is just looking in the bin. The problem is that the spoilage often starts in the core of the bin. It doesn't start on the surface or on the edge. So the earliest method of doing that is these grain probes, where you just essentially hammer in a big stick as deep as you can into the grain bin. And then there's a mechanism to open up a bunch of small chambers at different depths, and then you pull it back out, and then you can look at the grain and see if anything's going on, see if it's hot, test its moisture content, that kind of thing. There's obvious problems. These don't scale very well. The largest grain bins are now 130 feet in diameter. So you just can't monitor that grain very well. They don't scale. They're very manual. So but before grain bin imaging, this is kind of the current state of the art. Is so you hang cables from the roof of the bin, and these cables have temperature and sometimes temperature and humidity sensors on them. And they're a little point sensor that's just sensing the local temperature like a thermometer would, or the humidity like just like you would for the weather. So these are much better than probe sampling or looking at the top, because you're actually getting into the grain pile where the problems do happen. You can, these are electronic. So everybody who sells these bins has a website so that you can get the data off the website. You can read it locally with a handheld device, or you can check it out on a website as well. And you can also control your drying process a little bit better. So most bins, and all large bins, have fans that can push air through the grain, because otherwise you can't control it very well. Control the moisture content and the temperature. The problem with these current state-of-the-art sensors is that the biggest one is that the temperature and humidity sensors are very local. So grain is an excellent thermal and humidity insulator, so that you can have a problem. So one of the salespeople that I've worked with for many years, he said he was once in charge of a bin where it literally lit on fire. So he had a fire. There was a temperature sensor 4 feet away, and it wouldn't detect the fire because the insulation of that 4 feet of grain was good enough to make this grain was fine, but he could see smoke coming out of his bin. So that's the biggest problem, is that they're hyper local. And even though it's better than a probe or better than looking at the top of the bin, there's still large amounts of grain that just aren't monitored. And another large problem is that these cables hanging from the roof, when the grain empties, they put immense forces on those cables, especially in larger bins. And the grain bin companies that we work with, that the majority of the steel in the roof of a grain bin is actually there to support these cables. It's not there to support the roof and the snow load in the wintertime. So the technology that I'm going over today is kind of electromagnetic imaging or electromagnetic inversion. That's what the lab that I work at the University of Manitoba does. And this is, we have an antenna array. So there's usually something like, 24 antennas. That's what's in the grain bin. Each antenna will transmit and receive in turn at a bunch of different frequencies. And we pick how that's part of the art, is picking those frequencies. And you use that information of the scattered fields from some object you want to image, and you create an image of the electrical properties which is the complex permittivity of that object. Many of the algorithms that we use and the processes that we use were originally developed in the oil field industry. So in the oil field, you're regularly trying to see things deep underground where you can't use normal, something like X-ray imaging or traditional medical imaging technologies just won't cut it. They don't get enough signal through from your transmitters to your receivers. So you change the frequency of your electromagnetic radiation to get more signal through, and then you need a special kind of algorithm to make an image of what caused that scattering, and that's what we do here in the electromagnetic imaging lab. The key connection for doing this in a grain bin was provided by Dr. Pollywall at the Grain Storage Research Lab, is that for nearly a century, the complex permittivity is how grain moisture content has been measured at a grain elevator or on a farm. So every farmer has a grain moisture meter, and every elevator has a well-calibrated grain moisture meter that they use to test the moisture content of the grain, because it's one of the factors in the price. So that's been going on electromagnetically for more than 100 years. And that parameter, the complex electric permittivity, for those of you who aren't electrical engineers or familiar with the term, or a geoscientist who's used complex permittivity before. So the complex permittivity can be split into two parts. One is just the basic permittivity, which is related to the speed of the light in the material, and the conductivity is just the loss of the energy in the material. So the example I always use, you have a paddle, you stick it into a clear body of water, if the paddle looks bent, that's because of the speed of light changes from air to water. But if you stick that paddle into the Red River or the Assiniboine River, you're not going to see it, because the muddy water is absorbing the sunlight and it's turning it into heat inside that water, so you can't see it. And what allows us to use this imaging technology to monitor grain is that it turns out, we're lucky. It turns out that both high moisture and high temperature lead to high permittivity and high conductivity, and they both push the same way. So bad storage conditions are high moisture and high temperature. High moisture and high temperature cause the grain to sprout, which causes more moisture and temperature rises. And there's that positive feedback cycle I talked about. And both of those push in the same direction. It would have been really bad for us if they pushed in opposite direction. As the temperature went up, the permittivity went down. And as the moisture went up, the permittivity went up. That would have been very bad. We're fortunate that they push in the same direction. So the key thing is bad storage conditions and spoiling grain both cause high permittivity and conductivity. So that's the kind of key that allows this to work. Here is a schematic of what an imaging system looks like inside of a grain bin. So on the left here is just a photograph of one of the antennas that we use that they're mounted to the wall. Some of them are bolted, some of them are magneted. We've tried different mounting methods depending on sort of economic demand. But the antennas, they're kind of like a towel rack size approximately. So 50 centimeters tall. They stick out about 10 or 15 centimeters into the bin. Each antenna has to be cabled with an RF cable. So like a cable for, cable TV, it's a similar kind of coaxial cable that connects each antenna to a switch. with a control software and a computer in the box. I'll show a picture of that shortly. That does the communications and has the RF radio that does the RF measurements to transmit from each antenna and receive from all of the other ones, and the RF switch to do all of that. Here's a photograph of one of the early installs that we did. This bin is about 30 feet or 10 meters in diameter, 33 feet roughly. And, in this install, so the goal that we always have is to spread the antennas around the wall of the bin, outside wall of the bin as much as possible. You don't want to have a dead zone. It's much better just to get data from all possible angles. So we tend to try and spread them out as best we can. This system was bolted, so these antennas you don't see the cabling on the inside. All of the cabling comes on the outside of the bin and then runs back to our transceiver system that's stored, just bolted to the outside of the bin, basically. And this one here, just to give an example of size, so it's 10 meters in diameter and about 770 cubic meters in volume for this bin. This is the hardware, just a picture of what it looks like. So, on the left is the transceiver box that has, the control computer, and a whole bunch of custom boards for the RF switch, and then vector network analyzer is what we use for our radio that transmits and receives our signal that goes from, all possible antenna combinations. The center picture here is just a close-up of part of the RF board that is part of the switching and amplification that we use attached to that. And then we keep the power supply is kept in a separate enclosure that can be quite far away. There's multiple reasons for that, but one of them is just for RF noise. You want to keep your, especially on a farm where there's large industrial fans and other industrial equipment, the power supply can be very noisy from an electromagnetic perspective. So we keep it far away. And this kind of the power supply box also has relays to be able to turn fans on and off and do that kind of control, so that a producer or a farmer can sit at a computer and turn the fans on for all of their bins from far away over the network connection. So here's the kind of basic result that the system provides. So we have a computer model of the bin. I'm just showing a video of a 3D. It's a 3D image that comes out of it, but this is kind of slices of that 3D image. And we can provide things like a histogram of the number of bushels by moisture content. So this was a bin full of corn, and this is the estimate of what the moisture content of each bushel is inside of that. And that's useful because grain is bought and sold by weight, and you have to keep the moisture content low for safe storage, but you want to keep it as high as possible because you're getting paid for that weight. And if you've got 15% grain, you get more money than if it's 13% grain, because you just made 2% more by weight. And so that's worth a lot of money to be able to carefully control your moisture content, especially in a large bin. Now, the goal of this system is to, one of the biggest sales points for this system is that we can detect spoilage. The problem we have is that nobody industrial producer will let us spoil a bin of grain ever, for obvious reasons. So we've built many different scaled systems where we're able to just go in and spoil grain or add a bunch of water and monitor what happens. And this was one of the earlier ones that we did. So it's a barrel. It's about 240 liters of grain that go in there. We welded on a plenum false bottom floor so that we could pump air through this barrel. We put to just correlate, to give a second system of what we're using to correlate it. We use the temperature and humidity sensors here on this barrel, and then we made the grain really, really, really wet. And then we imaged the grain to see what would happen over 6 or 7 days as a fan dried out the grain. So here's a video of that result. And what we have is here just the number of days of drying. And what we did with this three-dimensional image is we got better results if we averaged it by layer, and it was a much easier thing to understand. But you can just see as time goes on with this system, the grain slowly becomes more dry. So it starts out above 22% moisture and then ends at 13% moisture, which is, goes from, this grain will spoil in a day or two down to you could store this grain, this wheat that was in this bin for months on end without worry. Then we have some plots of, how the temperature sensors compared with our imaging, and there's differences there, but overall you see how that works, and you can kind of watch this histogram change over time as to what happens with the moisture content. So it starts out almost all of your grain volume is up at the high moisture contents, and by the end it's dry. Here's just another little video to show that this is the same image as what was on the top of that last one, but just to show you that indeed there's a three-dimensional image that's being produced here, but we were just averaging it by layer, because the three-dimensional image, especially in this case from this test bin in the older times, it's really kind of there's a lot of spatial variation in the moisture content that is very hard to just look at and see what it's like. So we have a three-dimensional image, but this is just a threshold view of it to show you that that does exist and is there, shows the same kind of result, but it's more interpretable if we just average it by layer. Inside of some larger bins, we were able to actually bury some hotspots. We couldn't spoil the whole bin. We couldn't make the whole bin wet. That's very dangerous. So this here is just to show we went in this bin and physically buried bags of really wet grain to show what would, yes, could we detect a hotspot if it was indeed there? And of course, indeed, we can detect a hotspot. So that's just what this one shows. This bin's about 15 feet diameter. Here's another result is once we buried that hotspot, we just kind of let the grain sit there for a while. This was in the summer. Basically, we had there was a very bad insect infestation in this bin. And so we think that as these days went on in that little video, that indeed that we were actually detecting the insect activity, but we didn't. It was kind of an incidental insect infestation. And so we weren't able to sample it in time. We didn't know, so we weren't going in there to take samples of the grain with a probe or something to prove that, yes, indeed, we were detecting the insects. So this one, though, it was nightmare level of insects when this is done. When we went in here on day 9 and opened that lid, it's just a cloud of beetles that came flying out in your face. It was very, very ugly. And the grain was stuck to the outside bin wall where the bugs had eaten the grain. It was a very bad infestation. There might be some people more interested, rather than the actual grain, which I spent a lot of time talking about, just the architecture of how all of the RF side works and the signal processing side works. So, we have boxes on top of the bins that then communicate with each other, that have a cell phone network, that the inversion algorithm is done on the inversion algorithm is done on cloud computing. It's not done locally because it is a very large computation, and I'll talk about that in a second. Especially from a farming perspective, this is a very big computational problem. The results get displayed on a website that's constantly being refined and updated as well. That I can show some examples of in a minute. So our inversion algorithm, which is what I kind of specialize in, is that we have to build a computational model of the bin, which ends up being a mesh made of tetrahedral elements, and there's usually about 200,000 tetrahedral elements, and so the size of a tetrahedral just gets bigger in a bigger bin because you run out of computational resources. You can't simulate a large bin with the same size of tetrahedral as you do in that barrel, because it's just the computational problem becomes too large. We use a custom written code with this mesh to simulate the full three-dimensional electromagnetic problem. So full vectorial electric and magnetic fields have to be simulated. It's a finite element code that's custom written here in our lab. It eventually becomes a large, linear algebra problem, as almost all these computations do. And the linear algebra problem, I don't want to go into the details of the operator, but basically the core of it is we have a code that says, if you have this grain, tell me what the electromagnetic field should be. And that's called a forward solver. Now, the inversion algorithm, which is the other part, what you need to do is you need to say, well, I have a guess at what the grain is, and I have a measurement. You're going to simulate what the electromagnetic fields at your antenna should be. There's always an error between your measurement and your simulation. Then there's an optimization algorithm that goes and tries to create an image of the permittivity that causes those electromagnetic fields. And you keep optimizing until your measurement and your simulation are close enough. And that problem is called the inverse problem. And it's a very complicated set of rules and optimizations on how you do that. And the problem is that it takes a lot of computations because we have 24 antennas. And so every antenna is another full three-dimensional electromagnetic simulation. You have to put that in an optimization loop. So every time you're calling 24 times your full three-dimensional solver on this full three-dimensional structure. And so we tend to use the Amazon Web Services instances because they were the most economical when we were first developing this. And so it's kind of a 36 CPU, 72 gigabyte of RAM kind of processor. And so it's very expensive to put that dedicated onto somebody producer's site because they don't need it all the time. So it is definitely worthwhile to use the cloud computing services to do that computation. And the scans locally, it's highly variable. They anywhere from 1 to 20 megabytes of data per scan, which you might take 4 or 5 times a day, but we usually only image 1 per day because grain doesn't change all that fast, especially in the field. This, the website here puts the results, and there's all sorts of ways to slice and dice the images. Here's a bin that was relatively homogeneous, so the moisture content's very stable. And this is constantly being improved depending on the user feedback. So the net result is that we can have this thing in the field. We can generate a full 3D image of what's going on in the grain bin. It takes about 1 to 2 hours on these machines. Kind of costs ballpark kind of $5 per image is sort of just the computational cost that it does to do it. But the beauty of this architecture is it scales to thousands of bins because you just let Amazon deal with the scaling. So I'm hoping to save time for questions. And so just in conclusion, we've commercialized this within Manitoba. There's nothing like it to monitor grain in the world. We've come up with our own inversion algorithm using the high performance computing. We're always improving it. This group is still working together every day. And if anybody wants to ask questions now, I'd be happy to take them. And my contact is there if you would rather do that over writing. Thank you very much.
Thank you so much, Colin. I think everyone's going to agree with me here. That is fascinating. I never knew grain bins could be so interesting. I love the videos that you included in that presentation as a visual learner. That was really helpful for me to really understand what was going on. And can I just say, I appreciate that we're close to Halloween, but that nightmare level infestation that you showed, that's going to haunt me, Colin. Were you there for that? Were you actually there when that happened?
Yes. Yeah. I had to clean the bin out. I had to climb in and scrape all the grain off the bin walls and shovel it away because it's bad when it spoils.
So it's your nightmare, it's your Halloween nightmare then that you're going to relive. Okay, yeah, that was especially the video that accompanied that. I can only imagine what that was like in real life when you actually went to open that bin up. That is insane. So I have to say this is super interesting, and you definitely can see why you were shortlisted for this award. So I have opened up the chat. So if anyone who is watching has a question for Colin about GrainViz, please do let us know. This is the time to grill Colin and ask him any questions that you may have. And I'm going to start with hopefully a simple one. Can you give us a rough idea of how many bins this has been installed in so far?
Yeah, right now there's about, I think it's on the order of 30 to 40 bins that AGCO has it installed in. I mean, we installed it in 5 or 6 beforehand.
Yep.
They are very wary as a large company of, especially in the United States, there's a lot of litigation. And so they're very careful about opening wide sales until they're very certain that no grain will spoil once your system is installed.
Right.
So
being
They're going
conservative
quite
and
slow on
testing.
sales. Yeah.
Interesting. Oh, that's interesting to know, that kind of like litigation side of things.
Yes.
We have a comment that just come in. I'm not sure whether you saw that, but I'll read it out for you. It says,
Yeah.
"Awesome stuff, Colin. As a former co-worker of Braden's, it's really neat to see what he's been working on for the past number of years." And isn't it true? And I have to say, that's kind of one of the driving forces for this innovation award, is really shedding light on these projects that are happening, that are having a big impact in Manitoba and far beyond in this instance as well. There's a lot going on in this province that we just don't know about. And so I appreciate that comment, because yeah, that's kind of why we're doing this. Okay, so a question here from Martin for you. So how close is it to real time? If some hotspots are seen, if one can empty the good or bad parts of the bin separately, would you see the hotspot move down? Like, kind of how reactive can you be to how quickly the images are shown to you? I think
Yeah,
that's the question.
Yeah, thanks for the question. So it takes, basically the way it's set up right now is most images get to happen overnight. So things do tend to move fairly slowly in a grain bin. It's not like most electronics where milliseconds are a problem. So it takes 1 or 2 hours to generate the image. So I don't know if that's real time. You know, if you're in many applications, real time is in milliseconds, and so we're miles away from that, right? Once you do spot something, you're correct in that you would try and empty the bin to break it up, because if it's in little small bits, you can kind of stop that positive feedback process. We haven't been tested that because we haven't been able to, if you're going to build a test, you like, it's the big grain bin problem, where if it was in a big grain bin, we can't spoil the grain willy-nilly. It's just too much money. So you should be able to see it move as it breaks up. But one of the things that we have to do is the grain we need the grain to be stable at first because most of our images, we have some that aren't, but most of them are a differential image. So we want to watch it over time. So you want the grain to stop, be stable in stored condition, and then we can say this area is getting hotter and hotter and hotter and hotter. So that's the stable portion of our algorithm but we can't necessarily tell you if it starts right now with a really wet spot in the center. We have to wait for that wet spot to start to spread before it really is detectable, because it's a differential image to start out with. So maybe we see it, maybe we don't. You might have to wait for it to start to respoil again. And one thing I was just going to add, one other option is, rather than emptying the bin could you empty the good or bad parts separately? Most bins, especially at first, I'm not a mechanical engineer or a civil engineer, they have to start by emptying it from the center of the bin. If they try and do a side draw, there are some bins that have like draws where you can draw grain out in odd spots, like on the bin wall or down low. But when the bin is really full, I've been told by the grain bin designers, if you don't draw it from near the center of the bin, you can cause the bin to collapse, because you make an uneven load. And they're designed, the steel is very expensive, so they're designed as the grain should be symmetric as possible to force out to have the forces appropriately balanced.
It's really interesting, all these different challenges that you face. Hey, it's all the things you don't think about. Okay, we have time for one more question for you, and I see a really good one that's come in, especially considering that we are in Winnipeg. So Joy said, wonderful presentation. Do you use the same method to monitor grains during winter compared to summer? And I suppose a continuation of that is, does temperature affect this monitoring system in any way that you want to share with us?
Yeah, so to answer Gemma's question, the temperature, yes, the temperature affects the permittivity, which is why we can use this, right? As it gets physically, the temperature goes up, we can detect a hotspot. That's why they're called hotspots. Right. But so we could detect if the whole bin starts to get colder, then you could see that in the image, because it changes the permittivity. But it's the same method, whether it's the cold season or the hot season.
Right.
It doesn't. But yes. So yes, the short answer, it's the same method.
So essentially, if it's a really hot day, it doesn't affect it to a point where it makes the results misleading, is what you're saying. It still works in any conditions.
No, and grain is a very good thermal insulator. So if you're not blowing air through it, a hot day here or there, it doesn't matter. You can keep it frozen, or if it's 10 degrees Celsius, it'll be 10 degrees Celsius in January. It really is an excellent insulator.
That's really interesting. Awesome. So that's all the time we have for you for today, Colin. But before we say goodbye, is there anything else you'd like to say just before we say goodbye?
No, thank you. Thank you for the opportunity to present. And if anybody has any other questions, I'm happy to answer them. On my email is at the end of the talk, and is colin.gilmore@umanitoba.ca.
Awesome. Thank you so much for your time, Colin. Have a great weekend.
Thank you.
So everybody, next we are going to move on to our second shortlisted team. So we have Chen, Wang and Emerson Adajar, whose team was shortlisted for their innovative portable grounding mat.
Good day. This is Emerson Adajar and my colleague Chen and Wang. We are both here to present. We're from Manitoba Hydro, and we'll be presenting to you our portable gradient control mats. As a summary, at first we will be discussing the background. What is a gradient control mat? What's its use and what is its importance? Next would be the CIATI R&D projects. The findings of that R&D project and its objectives. Then we will slightly share to you the previous standards, tests on ground mats, and the proposed new test procedures. And after that, we will discuss to you the new test proposed under the CIATI GLP 3708. And also the test results on the available ground mats using the proposed test under that CIATI R&D project. Of course, we are presenting to you the ground mats that we presented to the industry. These portable ground mats that we just had a patent under the US and Canada. And after that, we will be also presenting to you the test results. How does it fare against the new test procedure developed under this the new CIATI R&D project? So to start off, what is a gradient control mat? So from the word itself, ground mat. So it's nothing different from the ground mats that you can see from playgrounds. So it's a mat that goes into on the ground. However, this is a life-saving equipment. Utility workers use them on their work area to protect them against high-touch potentials. It is placed under their feet, defining workplace, providing them insulation or equipotential zones. The portable protective ground mat provides a method for workers to establish an equal potential zone for multiple grounding applications. In Manitoba Hydro, we use our utility workers usually use them when they are switch operating handles. There are two available commercial ground mats in the industry right now. The first is the one in the left. This is a vinyl matting. This ground mat is manufactured with vinyl polyester fabric with high ampacity, thin copper braid sewn into a grid pattern. The braided copper on the grid connects to a termination stud on the corner of the mat. The ground mat is then bonded to the equipment being worked on by using a safe and reliable ground cable assembly. Now, this one onto the right, this is a utility in-house design. So it offers it offers the same protection, but it has a lot of limitations. So as you can see, there are two designs for ground mats. One is the fabric, which is the first one, which is made of vinyl, and the other one is the non-fabric. The fabric design gives elevation to the foot and thus providing isolation as well as grounding. Now, the non-fabric design is made usually of metallic, and then it allows the surface material, allows the foot to contact the surface material within a mesh. So records have shown that there has been multiple near misses in historically, and this has involving electrical workers while doing their work due to the hazardous touch and step potentials. Now, this has caused the attention of CIATI. So CIATI has created an R&D project to address the deficiency and the need to update the test and requirement for portable ground mats in order to better protect our workers. So in order for them to check the effectiveness, they decided to put in a new test procedure, and also if there are new improvements, new materials that we could use to use as gradient control mats. So before the CIATI GLP 3708, there is already the ASTM F2715 standard. This standard outlines the test procedure for ground mats, but this is only for fabric design only, not including the non-fabric design. And then this hasn't been updated since 2009. So there's really a need for updating these standards, and that's where it came the CIATI GLP Project 3708. With members from other utilities, from manufacturers, they have formed, and then they have come up with a new test method and test procedure. Right now, I will turn the presentation to Chen to discuss about the tests and the old and the new test method. Chen, take it away.
Yes. Hey, thanks, Emerson. So, okay, so as Emerson mentioned, like we have a couple like near miss incident like in the past, actually, not only from our utilities, made from the other North American utilities actually. So due to this kind of ongoing with safety concern, so that's why like Manitoba Hydro, along with other utility member, initiate this CIATI project to look into this issue and then to evaluate what kind of new test methods we should develop, to evaluate this type of design and in order to update the ASTM standard. So so that's why we like start evaluating different test methodologies, and then because the grounding mat has two streams, one is fabricate and one is non-fabricate. So that's why we design individual tests to evaluate a different type of product. So the first new test has been developed from this research is called a dielectric voltage test. So this test is designed to confirm the electrical insulation's performance of any non-metallic mat. So the test procedure including place a flat metallic plate with a white sponge on the ground mat. This is representing the worker's foot, so contact with the mat. And then we apply a voltage, and this voltage will slowly increase until the leakage of until actually the breakdown, the insulation is start breakdown actually. So this gave us the minimum breakdown RMS voltage on the dielectric mat. Next page, please. So for the metallic or non-fabricated mat, so the fault current test was introduced to confirm the grounding mat performance and the fault conditions. So the rationale of this test to confirm the largest fault current the grounding mat can safely handle and still maintain the safety features. So next page, please. So the fabricated mat was tested, like the orange versions, like as Emerson showed in previous slide. So come with a non-slip surface which braid copper wire mesh inside. So the test voltage was applied using a 50 kilovolt 60 hertz power source, and the voltage was slowly increased until the injected current reached 50 milliamp. That's the safety limit for the human we pick. Like usually is well accepted values in the CSA and then AESC standard. So the dielectric reading is about 4 kilovolt for a brand new match. Next page, please. But it's worth to mention the condition of this mat is very critical for the dielectrical testing. So we found some like previous used mat fail less than 1 kilovolt due to the like the wear out, the punctured hole, those kind of things. So it's really like depends what kind of condition you test on this particular mat. Next page, please. So for metallic mat, we test is made by basically these chain link fans, aluminum chain link fans, which like 30 millimeter mesh. The fault current rating is about 12 kiloamp, which is much less than the theoretical value, which is should be 23 kiloamp based on the calculations. So this reduction is mainly due to the weak connection between the copper braid wire and the aluminum mesh. So the mesh may be okay, but the connection is already break and it's arcing. So that's why it failed. Next page, please. I'll pass back to Emerson, who will discuss the next slide.
Yeah. So CIATI already identified that there is a need to have a better equipment to have a safer working environment to our electrical workers. With the currently available portable mat, in order for you to be certain, they need to inspect it every time at the start of each work. So because if those mats have small punctures, it degrades significantly the protection that it offers. So when we were discussing or when we were reviewing the results of the CIATI R&D project, it's like a eureka moment for us, for me and Chen. It's because we have an idea that could be a better material for the grounding mat, and also offers a portability, which is really useful for working areas, remote working areas. So when we were designing this, we went ahead with a non-fabric, which offers strength and easy inspection, uh, because you can really see the connection on each of the panels. And then also when we were designing on the design stage, the ASTM is already been revised to a newer procedure, higher energy levels, and then uh, one of the test requirements were one of the Manitoba Hydro employees involved is Jeff Laninga, who gave a very good point into developing this new test procedure. So when we developed this, we applied for a U.S. patent and a Canadian patent, and fortunately we got those two. So so this is the portable ground mat that we designed. Actually, there are already two versions. So the first version is the one in the left, and then the second version is the one on the right. So the first version is an attache case. It's made of aluminum, cut into 4x4 or 2x4, and then it is welded into a frame assembly. So this is really sturdy, and it offers a defined working area for our workers. So it those panels were attached with a hinge that is from running down from the bottom to the upper portion, so it will not buckle when workers step on it. So as you can see here, this is how the portability comes in, because it can be folded into like an attache case or like a picnic table. And this one can be locked with a spring mechanism. And then this locking mechanism can be used during working when it is spread out or not, so it will hug the ground more. It is perforated aluminum, so in order to limit the slip and trip falls. Now for the electrical bonding, we use 2 bondings per panel in order to make sure that all panels are in both equipotential zones. And you can see they're all just bolt connected for easy inspection. So every time the worker would start their work, they could easily inspect it, and then if there's something that they could easily remedy if there's some loose connections. Now to connect the bonding, to connect the ground mats into the equipment, it is equipped with a threaded ball studs, and then also we will be using these hotline clamps in order to have attachment or connection from the equipment to the grounding mat. Now, when we were designing this, we are continuously involving our workers, our field workers, and then with the help of them, we designed this version 2 of the grounding mat, which is much wider and a little bit lighter. So this one is also made of perforated aluminum, and then it can be increased by attaching in series all panels, and then it can be folded again into like an attache case, and then the braided wires act also not just for bonding but also as a hinge between the 2 panels. So it has a locking mechanism in order to secure it when you're trying to bring it to the remote work area. So, and then also we put in a steel wire just for to be able to carry it. And again, with a thread ball for attaching a hotline clamp, which is a must. Now, our test, since we already have these new standards, ASTM F27015, we have it tested to see if our grounding mat can be safe enough for workers, and then offer them equipotential safe zone. So the results of the tests will be presented to you by Chen.
Yeah, thanks, Emerson. So I will talk about the test procedure and test result on our design, like our in-house design might. So the previous CRT, like test procedure, and then the proposed by CRT has been adopted by ASTM standard F1275. And then particularly for the metallic one, we adopted the fault current rating test. So according to this standard, the minimum rating is 25 kiloamp RMS values under 15 cycles durations, and has to meet the high asymmetrical peak, depends on what kind of X over R ratios based on your system. So in additional to the standard, what we decide is we want to test all the way to 43 kiloamp as minimum. The reason behind the 43 kiloamp is matching the rating of standard fallout PPG cable used in our system. So we want to make sure the cable and the mat can match each other's, make a good pair. And then we also bump all the way to 54 kiloamp. That is the max allowable testing current in the high voltage lab. So we reach out the limit of the equipment. So both tests will be using X over R ratio of 30. Next page, please. The pass-fail criteria is all should be all the attachment point and any component shall remain secured connected during the test. We allow some minor arcing, but none of them should causing any significant damage on the any component or loss of cross sections. So resistance measurement shall be take like before and after the test, and it should be always less than 1 milliohm per foot. Next page, please. So this is the test setup we set up in the high voltage lab, and then the right hand cable connect to the positive, and then the left cable go to the ground, which is negative. And so the fault current will be injecting from the right to the left through the grounding mat. That mat will lift above from the ground, which is insulated from ground by those kind of wood plate. Next page, please. So this is showing a typical 43 kiloamp testing on version 1. And we connect between point A and point D. If you can play that. So as shown in this video, actually we tested all the way to 43 kiloamp, which is the upper limit of this 4-odd TPG cable. That's why the cable starts smoking because reaching the limit. And then the cable is we can see the cable start have some damage on the jack, on the outside jack, but the grounding mat still intact and there's really no arcing, no smoking. We don't see any damage. Okay, so this is a test result and observations on grounding mat version 1. So we test 3 current. One is 25 kiloamp. That's minimum requirement by the STM standard. And we test 43. That's our internal minimum requirement. And then 54, which is the limit of the testing equipment. So the version 1 show very good performance. It's passed all the 3 tests. There's no damage, no like minimum arcing we see, and we don't really see any smoking. And then the right hand side is showing the profile, the current profile. Go to the next page, please. So this showing the test result on version 2. Version 2 only test 2 current. One is 25 and one is 43. So both tests are passed. And then, but on the 43 test, we see some minor arcing flash and then smoke at the ball start. But when we did a resistance measurement, still within the limit. So we consider this test pass. And then again, the right hand side showing the test current profile. Okay, next page. So this is showing the some after test observations on version 1 mat, and so we see some small pitting and the small arcing marks between the surface of the grounding stud and then the surface of the ground mat. But besides that, we don't really see any really like noticeable damage. So we feel this one can even go higher than 54 kiloamp, but unfortunately we are not able to confirm that because the limitation of the equipment. Next page. So this is showing version 2. This is the flight versions, which is which is longer actually, but material is a bit thinner. So we can see some arcing spot, particularly at each joint point. And then we see some deformations on the boat. This is due to the material itself, actually, but we didn't see any major loss of sections. And then the resistance test still meet the criteria. Next page. Yeah, that's all for our presentations. And we open for question sessions.
Thank you so much, Chen and Emerson, for your presentation. I think your grounding mat is such a great example of how innovation can really benefit everyday work life, especially considering its safety applications, right? Because you're having a very direct impact on electrical workers' safety. This is not something you want to mess around with. So this is really fascinating to see the process that you went through, and also all those tests, like very, very thorough tests, and it's amazing to see the results from those. So thank you for sharing those with us today. If you do have any questions, you right there, Chen?
Yeah, sorry, some connection issues.
That's all right, you're still there. If you do have any questions you'd like to ask Chen or Emerson, please do type them into the chat. I think Emerson may be having some technical issues as well, so maybe we're just going to run with Chen today. But do type any questions that you have about the portable grounding mat or the process that these folks went through into the chat, and I'll be sure to ask them. I have a question for you, Chen. Can you tell us how this product has been used already in projects for Manitoba Hydro or outside of Manitoba Hydro? Can you give us a bit of information there?
Sure. So this product has become one of the tool in our toolbox, like for our maintenance people. And so in our company, we have different regions for maintenance groups. And so each maintenance regions already have some tools already, and then we start using that during like light switching operations, during set up the mini crane, those kind of things. Yeah, so it's become a handy tool, particular for remote areas.
Perfect. That's wonderful. Thank you for telling us how that's having a real life application. And now let's talk money. So how much does it cost to build these units? You detailed you had version 1 and version 2 that were quite different. Is there a cost difference between the two? What kind of difference are we talking?
Yeah, the cost difference is pretty. Definitely. It's very similar between these two versions, although the first version is beefer, but it's smaller, right? So it's all about the weight of the product. Aluminum price is based on weight, and then plus some welding costs and plus some copper. So in general, it's similar, and then it's cheaper than what the rubber, like the orange mat we bought before. Okay. So we do see some saving actually per mat. Yeah.
Oh, that's really interesting. So actually what you've created is cheaper than what was available for you to buy beforehand.
Yes, exactly.
Well, that's always good news. And obviously you presented today on version 1 or 2. I have to ask, is there plans for a version 3, or is version 2, are you happy with that? How's this going to progress in the future?
Yeah, so it's like the product keep evolving. Actually, we already have like a couple different designs, and then basically it's pretty much depend what kind of work we perform, or we got different feedback from the different crews. And for example, they want to have some particular design for broken conductor situations, and then to set up the equal potential zone in those kind of remote areas. Yep. So then they may need to different alternative, right? So that's why we're working with the field crew to making necessary changes. Yeah.
I love that. And I love the fact that you very quickly corrected yourself with EP and explained what you meant. So thank you for that. Yeah. I appreciate that as a non-engineer. So thank you. So I'm seeing a couple of questions come in. Here's a good one. Is this mat just for internal Manitoba Hydro use, or are there plans to sell this to other electrical power companies?
We are.
Oh.
Go on, Emerson.
We are open to that, because this is for safety of workers. This is what we designed this for. So we know that this will be really helpful to all electrical workers out there in all provinces in our country. So we're open to that idea.
Yeah, so we already shared some fundings within the utility forum between other Canadian utilities companies, and each company dealing with different issues, right? So yeah, so we share the ideas, the drawings, and then the material specifications, and then it's
very interesting. And there's a question here from Adele. She says, a great presentation. So thank you. Is there anything you're aware of in other utilities of a similar nature?
Yes, actually. So the chicken wire mat, like we showed before, is from Hydro One, which is our neighbor utility from Ontario. And then they do have some different versions in house design and from Alberta, from BC Hydro, those kind of companies. But we didn't see anything really like can taking full scale of fault current. That's the main driver for this project. We want to create some tools can handle the 100% of the fault in our system. So most on-hand design is perfect for de-energized work, and but we like to preparing something in case there is accident re-energizations during the work. So we still can make sure people will be 100% safe. That's why we did all the fault current testing in the high voltage lab. Like the video we show is below the make some smoke there. Yeah. So that particular weight, hold on weight, is simulate a lineman, right, which is roughly about 180 pounds. So we want to make sure the mat is still stable with somebody standing on top of it under fault current, and they won't, have any injuries.
Yeah, I love that video. That was one of my favorite parts. It was loud, but I loved it.
Thank you.
Thank you for sharing that. So I think that's all the questions that we have for you today, Chen and Emerson. Thank you so much for joining us. Do you have anything you would like to say before we say goodbye to you today?
No, thank you for the opportunity. We really like to present this one. Yes, thank you.
Yeah, thank you very much, too.
Well, thank you both for being a part of this session and for telling us more about your grounding mat. It's super interesting to see what's being created here in Manitoba. All right, so finally, we're moving on to our final one. It is now my great pleasure to welcome our final presenter of today, Paul Halipchuk, whose innovative turbine refurbishment technique at the Pointe du Bois generating station earned him a spot on the shortlist.
Good day, everyone. Thank you for joining my session today. My presentation will start with a brief primer on hydroelectric energy generation in Manitoba for the benefit of those that may not be familiar with hydro operations in the province. I'm then going to review the scope and methods used in a typical hydro turbine refurbishment. And finally, I'm going to discuss a new and innovative approach that I undertook for the refurbishment of a particular turbine at the Pointe du Bois generating station. Feel free to ask any questions you may have, and I'll try to answer them at the end. So Manitoba Hydro's current electricity generation capacity is around 6,000 megawatts. 96% of that is generated in 16 hydroelectric generating stations with a total of 112 turbine generator units. These hydroelectric units convert the potential energy of water stored behind a dam into electricity. The oldest plant still in operation in Manitoba is Pointe du Bois, which began construction in 1909, while the newest is Kiosk, which just finished in 2022. Since I'm going to be talking about a unit at Pointe du Bois generating station today, I'll take a few minutes to describe this plant. The site straddles the Winnipeg River with a concrete dam. Near the bottom of the photo is the powerhouse, which contains the turbine and generator units, while near the top is the spillway. The Winnipeg River normally flows through the powerhouse to generate electricity. When there's more water than required to generate electricity, the excess flows through the spillway. So now let's have a closer look at what's going on inside the powerhouse at Pointe du Bois. I should mention that although the general principle of operation is the same at all of our hydroelectric generating stations, Pointe du Bois units look somewhat different given that they were designed at the turn of the 20th century. First, let's change our viewpoint a little bit. So here's the powerhouse. Now imagine if we could take a section view right through the powerhouse. This is what we would see inside. So the inside of the powerhouse is separated into several areas. The areas shown in blue here represent the areas where the Winnipeg River flows through the powerhouse. Here is the turbine, which is located at the base of the turbine pit, and the generator located in the generator hall. When the unit is operating, water flows through the intake into the turbine and out through the draft tube. The spinning turbine is connected to the generator via a shaft, which then generates electricity. Now that we've seen the general operating principle behind the Pointe-du-Bois powerhouse, let's take a little closer look at the units inside. There are 16 main units inside the powerhouse with a combined capacity of about 70 megawatts. There are also two special, smaller generating units referred to as house units. These special units provide the electricity to light and operate the equipment within the powerhouse. Like all generating units, these machines require periodic overhauls to maintain their reliability. These units include a regulating mechanism to control the flow of water through the machine and act as a throttle. These mechanisms include a turbine governor, various linkages to transmit the governor action to the turbine distributors, and sets of what are called wicket gates arranged in circles around the water wheels, which must all act in unison to throttle the water flow through the machine and regulate the speed or output. As I said earlier, as these items wear over time, the stability of the governor control is reduced and the components must be renewed. Here you can see a little video of how all the components must work together to throttle the flow of water through the turbine. Here's a section view through that same turbine distributor showing the wicket gates arranged in a circle around the water wheel. In this view, the wicket gates are closed and the unit is stopped. When the wicket gates open in unison, water enters the distributor and flows through the water wheel, generating torque and power. Traditionally, mechanical unit overhauls are largely focused on piecemeal refurbishment of the wicket gate regulating mechanism components. On the main units, due to their large physical size and concrete embedded components, the removal of the complete distributor and replacement of those components is usually not economically attractive or practical. Here in this photo, we see a main unit turbine at the Kelsey generating station, where the turbine regulating mechanism has been completely removed. Here we can get an idea of the scale of some of these components on a main unit that make it more economical to refurbish the parts rather than replace them. These main unit wicket gates weigh about 2 tons each and stand nearly 11 feet tall. The complete distributor tends to be so large that assembling it in a remote shop and shipping it to site is simply not practical. The main unit distributors at Kelsey are over 30 feet in diameter, as we can see in this picture. In the past, mechanism components in the smaller house units have typically been refurbished following the same piecemeal procedures used on the larger main units, with the work being done mostly by our site staff. However, there are a few key differences between those big main unit turbines and the house units, particularly those at Pointe-du-Bois. First, the components are relatively small, so that the cost difference between refurbishing the existing parts and completely replacing them is typically small as well. And in some cases, replacement can actually be cheaper than refurbishment. Second, these components are 110 years old, and there is significant risk of finding unforeseen issues with the existing parts that could add cost and delay to the refurbishment, or may even be found to be beyond repair. And finally, our site resources are no longer adequate to perform the refurbishment work on these units, while also keeping up with the maintenance on the rest of the plant. While unexpected scope due to poor condition is not a critical issue when our site staff were refurbishing components, unknown condition makes it almost impossible for a contractor to bid a fixed price for the work. To overcome these problems, I developed a novel approach to reverse engineer many of the existing components and replace them with new ones. This reduced the risk of scope creep and helped the contractors to bid a fixed price confidently without significantly increasing the cost of the work. Further, the entire turbine distributor was sent to a single contractor for refurbishment and assembly in their shop, rather than refurbishing the parts in a piecemeal manner and assembling the turbine distributors at site. As an example of the process, here is a photo of some of the original cast steel wicket gates in the as-found condition. As you can see, they were badly corroded after 110 years underwater, some having large through holes rusted in them. The wicket gates have an extremely complex shape, and we had no original manufacturer's drawings of these parts to work from. By conducting surveys with a coordinate measuring machine on several wicket gates, I was able to produce a sort of histogram of the as-found gate shapes. Due to the rough cast nature and age of the gates, it was not surprising that they were found to be not all identical. By plotting the survey data all together, an average shape could then be determined, shown here in red. Using this average shape to create a 3D model, a new standardized profile was created for the replacement wicket gates. Here you can see some steel plate blanks and a partially CNC machine replacement wicket gate set. And here we have a completed replacement wicket gate ready for installation. Another example of risk reduction through component replacement was the turbine operating rings shown here. Each of the 14 holes in the ring must be evenly spaced for the mechanism to work smoothly. However, 2 of the holes were positioned very close to the split joints in the original parts. If during refurbishment the position of these holes needed to be shifted or they needed to be enlarged, the repair would have become very complex and also very costly. Instead, a new design was created that relocated these critical holes further from the joints, eliminating the risk of extra rework on the existing components. As I mentioned earlier, aside from replacing rather than refurbishing many of the regulating mechanism components, another departure from past experience was the complete assembly of the mechanism in the shop rather than at site. The benefits of this include a more controlled work environment, ease and speed of modifications should issues be encountered during assembly, and reduced site work effort. This being especially important due to the recent deficit in our site staffing. Although the turbine regulating mechanism is normally actuated by a hydraulic cylinder, we can see here that after a complete refurbishment, it can actually be moved simply by hand. This turned out really well. After the completed regulating mechanism assemblies were returned to site, they were quickly installed and the unit successfully commissioned and returned to service. This new methodology for refurbishing house unit turbines was so successful, it has been adopted for the overhauls of house unit turbines at the Kelsey generating station as well. And we can see here the completed turbine distributor for that unit in the shop after assembly. And that's it for my presentation. So if anyone has any questions, I'll be happy to answer those now.
Wonderful. Thank you so much, Paul. And you know what I love? Your presentation was so informative, but especially about how innovation can help like processes. So previous processes are just they're out of date. They're not working so well anymore for various reasons. And I love how you explored why they weren't working and how your innovation really helped solve those issues. So really interesting. And again, great pictures and great videos. I'm really loving all the visuals in today's presentation. So thank you so much. So again, everyone that's watching, if you have any questions, it's Paul's turn in the hot seat now. So pop those questions into the chat and I will start asking those. So what I want to know, Paul, is it all sounds great and it all sounds wonderful, but you got to dish the dirt. Tell us about, were there any unforeseen difficulties that you found with this new approach? Because there's got to be some, right?
Yeah, certainly. One of the issues we had, you saw in some of the photographs when we were machining those wicket gates. We started out with a fairly large, like a billet plate of steel,
Yeah.
and the bore through those wicket gates that they pivot about. There's the concentricity tolerance on those bores is very tight. And what we found was that because they started out by machining those bores, because they are a reference point for flipping the piece over to machine the other side, they would machine one side, and by removing that material, the plate actually relaxed a little bit. I guess there was some residual stresses from the rolling of the plate.
Mhm.
And then when they flipped it over and they tried to install the shaft, the axle that goes through, they couldn't get it to go in.
Didn't
And
fit.
yeah, so and we mentioned at the end of the presentation there how we're using the similar methodology for Kelsey house unit. What we've changed is we now rough machine the part completely on both sides and the bore to within, maybe a 1/16 of an inch. And then we go back and we finish the boring. And that way the part has relaxed before you do the final precision machining.
And this is it, right? I think that's a great example of engineering, right? You do something, you think it's going to work, it doesn't work, you come up with another way and you make it better. And yeah, that's great. I bet that must have been very frustrating when it first happened though, Paul. I can only imagine.
Yeah, it was not a good day.
I can only imagine that was not a good day. Okay, so actually we're talking about Kelsey. So let's do this question first. So curious why the house unit at Kelsey needs to be refurbished. This person is commenting, isn't it not currently in operation, Kelsey, or is it in operation?
Kelsey, yes,
It is
Kelsey,
in operation.
Yeah, Kelsey Generating Station was built in the 1950s and early 1960s. So yeah, it's currently in operation. And it has 2 house units just like Pointe du Bois.
And is the refurbishment of that happening now, or is that something that's planned for the future?
No, it's ongoing. In fact, they're just finishing putting that unit back together. Commissioning should start in a couple of weeks, and then that machine will be back in service.
And so this is probably a good time to ask the question, like, how long does the type of refurbishment that you're talking about, how long does that take kind of from start to finish?
Well, like for example, in the case of Kelsey, we were very much trying to hold the schedule to a summer period, because these house units are very critical for providing heating loads for various apparatus around the powerhouse in the wintertime. So we must have those units back in service before the snow flies.
Yes,
very so important. Yeah, 5-6 months maximum. That's all you've got.
Okay, that makes sense. Somebody here is asking, perhaps they missed it. Did you find any old drawings, say in a drawer, for example, to help guide your new CAD drawings?
So there was only one drawing available for these units, and it was a general arrangement drawing. From 1909, I think that was the date, and it was a Swedish company actually that supplied those units for Pointe du Bois. But that's it, just that one drawing. Everything else had to be reverse engineered from scratch.
That's a lot of work.
it was a big undertaking, yes.
Yeah. So another question for you: do the house unit control mechanisms use mechanical or digital governors?
They originally, of course, were mechanical governors because when these units were built, there was no such thing as digital controls. The governors on these units were changed out, I believe, in the 1990s to a digital governor controller. So like a mechanical governor, think of like in cartoons and on really old steam tractors, you see the little spinning, like 2 weighted balls spinning around an axis. That's like the basis of a mechanical governor. And digital, of course, that's all done with circuits, and it's beyond me. I'm a mechanical guy, so that's out of my wheelhouse.
And you know what? It's lovely to hear people say that as well, because you realize how many people it takes to make this whole thing work, right? Like, yes, you have your area, but you know, you need those other people in your team. Yeah, totally. You do not function alone. Okay, I think this is going to be the last question that we have to you, and it's a bit of a second parter to the old drawings comment. So how did you average that profile data from, okay, so this says Faro, F-A-R-O, could you explain what that means? And does the Faro software do it for you?
Okay, so they're Faro is a brand name of survey equipment. The photo we saw of the surveyor using that gun looking thing, it's attached to an arm.
Yep.
And as you move the arm around and then you touch the tiny little tip and then you pull the trigger and it surveys a 3D point in space. And if you do that enough times, you get a profile of the component. I have to admit that there was so much scatter in that data that I brought up all of those survey results on AutoCAD on my screen, and I used those two bores that we see, the bore centers, as the reference points. Like I overlaid those all, and then I just started drawing red lines through the scatter, and wherever they connected well, and you got to make sure that things are smooth and tangent. It was kind of a little bit of artistry there, I suppose.
And that's part of it as well, right? That is, and the person says, I see, good method. So thank you for explaining how you did that. So that's all the questions that we have time for you today, Paul. So thank you again for presenting. Would you like to say anything before we say goodbye to you today?
Well, I guess I thank Hydro for the support and giving me this neat opportunity to work on this interesting and challenging project. And thank you to Engineers Geoscientists Manitoba for the shortlisting for the Innovation Award.
Well, congratulations, you definitely earned it. And thank you again for joining us today, Paul. So I just want to say a huge congratulations to all of the 2022 shortlisted nominees, and a big thank you for them all for taking part to present their projects here. It's so wonderful to hear about the innovative work that's happening here in Manitoba, and all of you nominees should be very proud of your achievements. So I can reveal, drumroll, that GrainViz was awarded the 2022 Innovation Award, and you can find the full award citation on the association website under awards. So it's just www.engomb.ca/awards. So you can go and actually read the citations of GrainViz, of this year's Innovation Award winner, as well as the other awards that we give out each year. So while you're there on the website, we do encourage you to check out the eligibility criteria for the annual awards and start thinking about potential nominations. If you can believe it, nominations are going to be opening for 2022 shortly. We only just awarded them 2 weeks ago, but the cycle is beginning again. So there will be an announcement when nominations open in the next few months. And on behalf of the awards committee, we would love to hear from you. And another group that would love to hear from you is the Ingenium task group, who are central to sourcing the presenters and content that you've seen today and all of this week. As we come to the end of the 2022 Ingenium professional development seminars, we are already looking to next year. I already have a list of potential presenters. You'll be receiving a survey next week, and your feedback is crucial. So if you didn't like something, please tell us. But if you love something, do me a favor, tell a colleague, because registration will be open until early January to access all of the recorded sessions, including this one. And there's also the exclusive on-demand sessions I mentioned at the beginning, which haven't been broadcast at all. They're only accessible through the Ingenium Hub. So all of that content is available from now until mid-January, and anyone can sign up at any time to access them. So I'd like to take a minute now to thank all of our moderators for this week who volunteered their time to be the face of the conference. Moderating can be very nerve-wracking, especially for engineers and geoscientists who do not do it as part of their day-to-day job. And I'm sure that you'll agree that they all did an amazing job of handling all of your questions. So thank you to Andrew, to C, to Tanya, and also to our special guest moderator, Mike Gregoire from the association, who moderated the session before this one. So behind the scenes, you never see behind the scenes on events, but I got to say some thank yous. I'd like to thank our operations team for their support with this event. Angela, who has been off-site as our backup for in case for whatever reason we lose critical power here at the association, and we wouldn't have lost Ingenium because of her, so thank you. Chella, she's been running our social media. You've probably seen some posts from within our beautiful new studio this week. If you haven't, go and check them out. Follow us on Instagram and Facebook and see what we're up to on social media. A special thank you to Heather at our front desk here at the association. She's been handling all the registrations and all the last minute queries. For those of you out there that was calling and emailing on Tuesday morning saying, I can't find my access to the Ingenium Hub, you probably heard from Heather. So huge thank you to her. She does a lot of work for Ingenium and we appreciate it. Special thank you to Andrew. The website that you went to, the Ingenium Hub, that is all Andrew, our web developer. And he does a lot of work on that. So thank you very much to him. And also I'd like to give a special personal thank you to Danielle, who is teching this session today from the other side of the screen for helping me out while I moderated. And thank you all for attending this presentation. Did you miss any part of the session? Don't forget to check out the Ingenium Hub's on-demand library for recordings of this and all of our live sessions, as well as that exclusive on-demand professional development content. Thank you for attending Ingenium 2022.
Thank you for watching. Visit the Ingenium On Demand library for more exclusive content.